Welcome to my video series on basic operations management. Now, just a reminder that these videos are geared towards individuals that are new to the field of operations management. Therefore, I will only be covering beginning and intermediate level content. If you are looking for extremely advanced topics in operations management, these videos may be a bit below what you are looking for. However, if you are just looking for the basic overview of important topics in operations management, then these videos should be for you. So without any further waiting, let's go ahead and begin our topic for this video. In this video, we will be talking about project management, and more specifically, how to create network diagrams for projects. And of course, we'll talk about what that is here in a few minutes. But as always, I like to begin with an example. And actually, this example is actually true from my life. A couple months ago, my father and I replaced a 30-foot section of wood fencing in my parents' backyard. The old fence was kind of falling down. It faces the wind, so it gets blown over time. So it needed replaced. Now, of course, this is actually a fairly involved project for something that on the surface would seem so simple. Now, the question is, how should we tackle this project given that, 1, the old fence had to be torn down, 2, the old concrete footings for the posts had to be dug out of the ground, which was real fun. The new posts must be then inserted into those holes, and then the new posts must be set in concrete. That concrete has to cure, has to set. Then the lateral support boards that go horizontally have to be attached to the posts. And then the actual fence sections must be placed on those support boards or hung on those support boards and then fastened into place. Then, of course, we have project cleanup. Otherwise, my mother would kill us both. Now, due to both of our work schedules, we could only work on the fence a few hours per day. So we really had to think about how to plan this project. Now, like any project of this sort, things have to occur in a certain order. There are just certain things that have to be done before other things can be done. So here's what we know about our fence project. Of course, the old fence had to be torn down. Duh. We can't really go anywhere without doing that. The old concrete footings had to be removed because the new posts were going into those holes. The new posts had to cure for a couple of days. That way we knew our posts were securely in the ground before we hung the fence on top of it. And of course, the support beams had to be attached because if those aren't there, then the fence has nothing to hang on. And of course, the project cleanup, well, we can kind of do that as we go. So we try the best we can, but we don't have to wait until the end to do that. We could do that at any time along the way. But the important thing to keep in mind is certain things have to happen in a certain order. We cannot complete certain steps until something before it is complete. And that is at the heart of what we're going to talk about today, which are network diagrams and events that have predecessors that have to be completed before we can continue. So think about these very complex projects. Installing the computer network at a large university. So when you're like I was at a university that has 40,000 students and it's massive, think of installing all of that computer network connectivity. Now, of course, we have bringing soldiers home from a war zone. We have logistical considerations as far as when the troops come home. Of course, we have to move equipment, and we have to reallocate certain things. So that's a very complex project, of course. Building a skyscraper, things have to occur in a certain order. Of course, we cannot put the needle on top of the skyscraper, in step 2. That has to be one of the last things we do. And of course, creating or building an entire computer operating system. So we have to build it from the ground up. We have to have certain functions in place before we can call those functions in more complex code. So all of these projects and many others require inputs such as time and money in various resources. And of course, in business situations, we are trying to minimize those inputs. So we want to follow the path through our project that can minimize time, that can minimize, of course, cost, because that's associated with time, and uses minimal resources. Now, when thinking about how a project can proceed, there are three fundamental ideas to keep in mind. Some activities in the project must be completed before others can begin. Some activities require several activities to be completed before others can begin. And some activities can occur alongside or parallel to other activities independently without any interference. So think about the steps in constructing a house. Of course, you have to get all the permits and everything before you can even think about starting to build your own house. And then you have to clear the land, and you have to make sure all the sewage lines and water lines and things like that are installed under the ground. Then, of course, you have to build the foundation, and then from there you build up, and you frame the house, and then you work on the inside of the house, and you make sure the roof is on, and all that kind of stuff. Now, you can think of all that in terms of what has to occur in a certain order, and that should make intuitive sense, okay? We're not going to, shingle the roof before the walls are up. It doesn't make any sense. So just think about everyday things, everyday projects you're familiar with, because really what we're going to talk about in business is no different. So how can we visualize the flow of a project, including prerequisite activities and concurrent activities? And all that means is those are activities that can occur at the same time because they don't interfere with each other. And the title of this video is the network flow diagram. Now, there are a couple of different kinds of flow diagrams. I use one that's called activity on node, or AON, for my network diagrams. There's an activity on arrow convention, but I don't prefer that one very much because it involves using dummy nodes and stuff like that. So I stick to the activity on node. You really don't need to know about a whole lot about that. Just know that there are a couple different ways to do this, but I prefer the one we're going to do today. So let's go ahead and take a look at AON networks. So here's our first simple example. So we have a diagram on the left. Of course, we have three pink circles that are connected by arrows. And here's what we know about this diagram. We have three activities which are represented by nodes A, B, and C. Now the arrows are what is really important here. The arrows tell us that A must be completed before B. It also tells us that B must be completed before C. And of course, logically, A must also be completed before C. So this is like a gate system. So we go to activity A, and we complete it, then the gate opens to go to B. Then we get to B, we complete that activity, then the gate opens, and we go on to C. So everything requires whatever we're doing to be completed, then we can go on. Now here we have example 2. In our diagram, we have the same three nodes, A, B, and C, but the arrows are a bit different. So what do the arrows tell us here? Well, the arrow from A to C tells us that activity A must be completed before we can go to C. The arrow from B to C tells us that activity B must be completed before going to C. So therefore, logically, activities A and B must be completed before C can begin. Let me say that again. Before C can begin, activities A and B both have to be completed. So here's example 3. Again, we have A, B, and C. And let's pay attention to our arrows in this one. So activity A must be completed before we can begin in B. And activity A must be completed before we can begin in C. So therefore, logically, activity A must be complete before we can go on to activity B or C. So think about this for a second again. Let's say we're in activity A and we complete it. All of a sudden, two gates open up. One gate leads to B and one leads to C. Now we can go ahead and go to B if we want. We can go ahead and go to C if we want, or we can go ahead and go to both. But the main thing to keep in mind is that the completion of A is what opens up the gates to B and to C. Now B and C don't have to begin necessarily at the same time. The path is just open once A is complete. So here's example 4. This one's a bit more complex. We have lots of arrows going on here. So now we have A, B, C, and D. So let's go ahead and look at our first one. Activity A must be complete before activity C can begin. So that's the arrow from A to C. Activity A must be completed before activity D can begin. That's our arrow from A to D. Activity B must be completed before D can begin. That's our arrow from B to D. And activity B must be completed before activity, that should say C, can begin. Okay? So, what does all this mean? Now, let's say we're in A and we're done with A. So two gates open up and we can go to C and D. Now let's say we're in B. We complete B, two gates open up, and we can go from B to C and B to D. Now, because A is a predecessor of C and D, and B is a predecessor of C and D, C and D cannot begin until both A and B are completed. Let's think about that again just for a minute. Let's say we get done with A before B. So the gate opens up and we can go from C or D. Can we begin C or D? No, because C and D are still waiting on B. So then B gets finished, its gates open up, and then we can go to C or D. So C and D cannot begin until both A and B are complete. And if you think of it like a gate system, it's a little bit easier to visualize in your mind. So here's example 5. We have the same 4 activities, A, B, C, and D. Now if we look at each arrow, activity A must be complete before C can begin. Activity B must be complete before C can begin. And activity B must be completed before D can begin. So therefore, logically, activity C cannot begin until both A and B are completed. Because you see, C is dependent on A and B. And D cannot begin until B is completed. So the arrow from B to D makes B a predecessor to D. Now, we could finish B first. Okay, so we have some people working on activity A, and we have some people working on activity B. We could finish B first, and then continue on to D. Because the only thing D is dependent on is B's completion. However, if we're at B and we're complete, we can't go to C yet. Because A also has to be complete for us to go to C. Or we can't begin on activity C until A is complete also. So again, take a second, pause the video, and think about what we're doing here. We're just setting up a system of precedence. And the arrows indicate what has to be completed before we can begin where our arrows lead to. And finally, we have example 6. So we have our same 4 activities, A, B, C, and D. And of course, A must be completed before B can begin. A must be completed before C can begin. So that's there towards the bottom. B must be completed before D can begin. That's our arrow from B to D. And of course, C must be completed before D can begin. So therefore, B and C are dependent on A being completed. So if we're in A, we complete it, 2 gates open up, and we can go to B and to C. Now if we're in B, once we complete B, 1 gate opens up and we go on to D. Now if we're in C, 1 gate would open up and we can go on to D. Now remember, we cannot begin in D until the gate in B and the gate in C are open. So if we finish either B or C first, we have to sit in the other one and wait until the other is complete. And then at that time, that gate will open up, and then they can proceed on to D. So here is our penultimate example in this presentation. So we have a paper company, the Milwaukee Paper Company, and they have to install a complex air filtration system according to new EPA standards. So on the left-hand side, we have our activities, just like we had our nodes in our previous example. In the middle, we have a description of what is going to happen at each node. And then on the right-hand side, we have the predecessors for certain activities. Anything that has a predecessor cannot begin until whatever its predecessors are complete. So we have things like build the internal components, modify the roof and floor, construct the collection stack, etc., etc. So we have a number of activities, and some of them have immediate predecessor activities that have to be completed before they can begin. So let's go ahead and open up a drawing program and actually in real time draw the network diagram for this problem. All right, so let's go ahead and start drawing our network diagram for the Milwaukee paper problem. Now off to the side, out of view of the video frame, I do have all of our nodes prepared ahead of time. That way you don't have to sit and watch me draw a bunch of circles and color them in and things like that. Now if you notice in the top left, I've gone ahead and copied over our table from our presentation. And that way we can see exactly what activities we're going to put in our network without having to flip back and forth between the presentation and this drawing. Now we're going to start our network with a starting point. And I always do my starting points with a green circle, and ST means start. So we'll put that there. Now let's look at our table. We see that activity A, build internal components, and activity B, modify roof and floor, have no immediate predecessor activities. So those 2 activities will start our network, and they will not rely on anything before them. So we'll go ahead and move those over. So we have A and B. So from our starting point, we are managers at the Milwaukee Paper Company that are in charge of this project. We could assign a team to building the internal components, and we could assign a team to modifying the roof and floor, and neither one of those activities depend on some previous activity. So let's go ahead and look at activity C. Construct the collection stack. Now you will see that activity C is dependent on activity A being completed. So apparently we have to build the internal components of our air filtration system before we can construct the collection stack. So C has the immediate predecessor of A. So let's go ahead and move C to after A. Now when you do these network diagrams, they will not always be pretty and neat when you go to draw them at first. So sometimes you have to do a rough one and then go ahead and rewrite it in a more finished fashion. Let's go ahead and look at activity D. Pour concrete and install the frame. Now you will notice that activity D has 2 immediate predecessors. In order to pour the concrete and install the frame, we have to have the internal components built and already have modified the roof and floor. So let's go ahead and take activity D and move it over. Now I'm going to pause here to draw in some arrow lines. Now my lines will not have arrowheads on them, but just keep in mind that we're moving from left to right at all times. So let's go ahead and draw in some paths. So we know we can go from start to either A or B. Doesn't make a difference. Now we know that activity C has the immediate predecessor of A. So in order to go to C, we must have A completed. Now let's take a look at D. For D to occur, we have to have A and B completed. So we need paths to both of those. Okay, so from the start we can go to A to B because neither have immediate predecessors. Activity C requires that activity A be done, and activity D requires that A and B get done. So let's think about this for a second. If we go on and do A and B at the same time, but maybe we get done with A bit earlier, which one can we go on to right away? C or D? Well, we can only go on to C immediately because D has to wait on the completion of B. So you kind of see how these are put together? Let's go ahead and continue. Now activity E is build the high temperature burner, and that is dependent on C being complete. So we know that it has to go somewhere around C. Now activity F, install the pollution control system, is also dependent on C being completed. So let's go ahead and move that over. Now the question is, why did I put F above the E? And that's because if I look at E and F in our table, and then I look down at G and H, F has no connection really to anything else except to H at the end. So I'm going to go ahead and put it above because we will be ending on H, and actually that will make more sense when we're done. So let's go ahead and draw in some lines. We know that F is dependent on C being completed, so we'll attach those. And E is also dependent on C being completed, so we'll attach those. So once we complete activity C, we can go on to F and or E. So how about activity G? Install the air pollution control device. Well, in order to do G, D and E both have to be completed. So let's go ahead and move G over. We'll put it down here somewhere, next to D and E. And again, I'm placing them next to their predecessors. So that's kind of how I'm deciding where I place my circles. So G is dependent on D and E being complete. So we'll go ahead and connect those. There we go. And now we have one more, and that is H, inspect and test. And that is dependent on nodes F and G being complete. So H will of course go out on the far right. So we'll move that over. There it is. And then we got to connect F to H and G to H. And there we go. And that is our completed network diagram for the Milwaukee paper problem. And let's just review how we proceed through this network. So once we start, we can begin with either A or B. There's no restriction on where we can start. Now once we get done with A, we can go ahead and proceed to C. No problem. Now going to D depends on A and B being completed. So D cannot occur until both A and B are done, whereas C can be started once just A is done. Activities E and F can only be started once C is complete. Now if we go down to G, look at its connections. G can only occur once D is complete and E is complete. So both of those nodes have to be complete before G can occur. And then finally, our final node, H, can only begin once F and G are done. So each path leading to a node is its dependence. And you just have to follow along the path to figure out where you can go depending on what has been completed before it. Okay, so let's go back to our presentation. Whew, that was fun, wasn't it? Well, that was a fairly modest network diagram with, only 8 activities in it, 6 of which had predecessors. So you can imagine even more complex projects with numbers of predecessors that kind of circle around and do all kinds of crazy stuff. But that is just a good example to show you, 8 activities, 3/4 of which have predecessors and how they're all connected. Now, one thing we did not talk about in our drawing or in our previous example of this problem was the time we are at each node. And believe it or not, in this video, we're not going to talk about that either. That's going to be saved for our next video. But it will show you just how the time is laid out for each node. Activity A, which is build the internal components, is going to take 2 weeks to complete by our estimates. Activity B, 3 weeks by our estimates, and so on and so forth. So as you can see, the completion time for each project or each activity, it varies. So as you can imagine, if you think of our system of gates again, if we are working on an activity that has some predecessors to it, it's going to depend on when that gate opens so we can go on to the next node. And that will, that through our network, that's going to create a sort of a crazy system of gates opening at certain times so we can continue forward. And actually in the next video, we're going to talk about a really cool way to figure out how we can calculate that and what activities in our network we can wait on a little bit. We call that slack. And what path through our network is the absolute critical one that has no slack to it. So we'll talk about all that in our next video. But I just want to show you that each activity also has an associated time. And you can think of that time as how long we have to wait in that activity until the gate opens to go wherever it leads to. This graphic is simply the times from our previous slide drawn into the actual diagram. So you can see right off the bat, I'm not going to go into this in depth, but you can see right off the bat that if we send a team to activity A and we send part of our team to activity B at first, because we can start in both, there's no reason we can't do that. Activity A is going to be completed in 2 weeks, but activity B is going to be completed in 3. So the gate from A is going to open a week before the gate in B opens. And because of that offset nature of when things open and you can proceed, that's what makes these problems, fairly complex. If they all opened on 1 week intervals or something, it wouldn't be overly complex, but they don't. That's not real life. So those are the times written onto our diagram, which we will tackle in our next video. Okay, that's review, and then we'll finish up. So when thinking about how a project can proceed, there are 3 things you always have to keep in mind. Some activities have to be completed before others can begin. Some activities require several activities to be completed before they can begin. And some activities can occur alongside other ones because they do not interfere. They can run parallel or concurrently. And we can use simple network diagrams to show the relationships between all those activities or nodes. And most importantly, what activities have to be completed before we can proceed to the next activity in our project. Okay, and that is it for this video. Again, thank you very much for watching, and I do look forward to seeing you next time. Take care.